Hello everyone, welcome back to LeetCode Daily Live where I do the daily question, raw and uncut. So before we start today, I'm getting close to 100 subscribers, so I want to do like a special video. So tell me whether you guys want a range tree tutorial. So range tree is like I would say a very useful data structure, but it isn't really taught anywhere, I feel like. Or I can talk about how I usually solve LeetCode questions. So yeah, let me know below what like which one do you guys want more, or if you have any other ideas, tell me below. I'm happy to try them as well. So yeah, so let's get started. So we have a hard today. It's called find the maximum sum of node values. So let's see what we are given. So we are given an array of numbers and int k and also some edges. So yeah, because we have an undirected tree, so that's how it is represented, I think. So let's see the size. So oh yeah, it's here. So we have 20k amount of numbers, and k could be right. K could be well, basically any integers, and then you have and each number inside can also be any integer. Edges length, right? Yeah, because it is a tree. So if you have n nodes, uh, you have n minus one edges for a tree. If not, you have cycle and it wouldn't be a tree anymore. So yeah, edges length. So that makes sense. And then yeah, the edges. So the nodes are zero indexed basically. That just means also edges forms a valid tree. Okay. So you're also given a positive integer k. Yeah, I think that's just kind of what we went through. So Alice wants the sum of values of three nodes to be maximum, and she can perform any number of times, like with the following operations. So she can choose any edge, connecting the nodes, and update their values as follows. Huh. So right, so you do XOR on the number k, or and you can do XOR on the other number. Yeah. So return the maximum possible sum. So basically, for any operation, you can choose an edge, and you can, and for the two nodes that share that edge, you can do XOR k on them. So we want to return the maximum possible sum after performing any number of times. So there are no limits on how many you can perform. Yeah, but I'll talk about why that doesn't really matter later on. So let's just look at some example first. So if nums is 1 to 1, and k is equal to 3, so I'll put a 6 here. So Alice can achieve the maximum sum of 6 using a single operation. You just choose the value 0, 2. Wait, actually, what are the values? It should be nums, right? So choose the edge 0, 2. So nums0 and nums2 become 1 XOR 3. So it becomes 2, and then wait, but there's a 0 there. Why is there a 0 there? Wait, is the tree and looks number? Oh, is number 0 to n minus 1 actually? So what are nums here then? What does nums do? Yeah, the value of the node number I. That's what I thought. So why is it 1 to 1 at the beginning? I guess it's like maybe I will draw it out. I think what it means is it has like 1, 2, and 1, and then if you look at the edges, maybe I'll make this smaller. Yeah. So if you look at the edges, it connects 0 and 1, 0 and 2. And what it is suggesting is if you XOR this edge, well, 1 XOR 3, well, which is like 1, 1, it's going to be 2, right? Because like it's 1, 0. So 0B, so that'll be 2. So that'll also get turned into 2. And it is saying that it can't be any bigger, basically. Right. So it can be shown that 6 is the maximum achievable sum. Yes, I agree with that, yeah. And the example 2, so you have nums 2 and 3, k is 7, and you have like one edge connecting them. Yeah, I guess like the image here is very it's very misleading because it really should be a 2 and a 3 here, but it is writing like which index they are. Yeah, I think I have a rough idea on how to do this, I think. So yeah, let's talk about my observation so far, right? So the first thing is maybe I will make this a bit bigger again so you guys can see better. Like this. Yep. Okay, so let's talk about the observations. So the first thing is any number XOR a number, and then you do another XOR again. Because XOR is associative, so that means like I can do this operation first, and it will be the same as doing this first, and then doing the third one. So because of that, X XOR K is actually going to give you 0 because like they have the same binary digits, right? So they will always cancel out when you do XOR. So remember, XOR is whenever you have the same binary digit, it becomes 0. But if they're different, it will become 1. So that's why, and any number XOR 0, it will just keep its digits, right? So like if it is a 1 already, it will be different from 0. If it is 0, it will still be 0, and so on. So that's the first observation. The second observation, actually, so what does the first observation lead to? Well, it means that for any node, you either do one XOR on it, or if you do an odd number of XOR on that node, it will become another number. So let's call that like X. But then if you do XOR again, it goes back to X. And like one of these number, like for example, if X is bigger than, like if big X is bigger than X, then yeah, it will be good to like turn it into X. But then if big X, so if the XORed X is actually smaller, then we want to keep the original X, right? And we won't get any other values. So that's the first observation, right? Yeah, the second observation, I kind of forgot what the second observation that I had before is, but yeah, maybe I can just talk about my kind of initial idea. So we want to get the maximum possible sum, right? So like for example, if we have an X here and then we have a big X here, and if we turn it into big X, it is better. That will make you kind of think about greedy, but then I don't think that will work, because when you are changing like the current X, you're also XORing with another number, right? And that number could be affected even more. Maybe I can think of an example. So if you have like 1001, XOR. So let's say k is like 111, right? And then you have like another number 1111, and they have an edge between them. So if you do XOR on this number, yes, it will become 1110, which is bigger. But then when you have to XOR the second number, it actually becomes 1000. And if I turn them back into decimal, so this would be 9 and this would be 15. This is going to be 14, I think, and that'll be 8. Yeah, so like in this case, it doesn't actually change anything. Yeah, actually, I'm not too sure whether the sum is the same um or if it is different. So yeah, we like when we XOR two numbers, is it always the same? I don't think so. Yeah, I think there are cases where they're like different. Yeah, maybe 111 is not the best way to go about. So maybe let's do like 110 and see what happens. So if it is 110, actually this will become 1111, and then this would become like 1001, right? Um, so yeah, actually in that case, both of them will get bigger, which is good. Yeah, I'm just trying to think of a case where it doesn't get better. Maybe 101. Would that work? So this would become like 1010, and then maybe I could turn this into a 1. Yeah, and then we turn this also into a 1. Oh wait, we got the same number now. Um, let's think about the best way to go with this. Yeah, so in this case, so in this case, 101, it will be like 1010. So actually, the top number becomes smaller. But is there a way that after XORing this, the number actually gets bigger? Maybe something like 1001. So that will become I guess like 1. I'm not good with my binary and XOR, so you guys will have to bear in mind. Well, you guys will have to bear with me. Yeah, actually, even in this case, well, actually, yes, it will become bigger in this case, right? So what do we have on the left here? Yeah, we still have 9 and 15. And then on the other side, we have like 12 and 10. Yeah, okay, so this is an example. So I finally got an example. So this is like 22, right? This is 24. So actually, like if we just look at the bottom number, yes, the XOR makes it bigger and better, but it doesn't actually make the sum it doesn't make the sum bigger like in the overall picture. So that's why that's why I don't think it will be greedy. But because of this property up here, like where if you do 1 XOR, it becomes another number. If you do 2 XOR, it becomes back to itself. Because of this thing here, we actually only have 2 states. So that's why I'm thinking of a 3DP instead. So how that will work is so for each edge, so like let's say we have the 0, 1, 2, that kind of case, right? Well, I think it's actually 1, 2, 1, right? If I remember correctly, it's actually 1, 2, 1. So in this case, I think like we want to get the maximum from a subtree. So this is like the subtree, right? Um, like if we just XOR on it, but then because the top also connects to the to the next number, we have to think about how we merge these different cases together. So if k is equal to 3, if you XOR 2, that's going to be smaller because 1, 1, 0. So if you XOR 2, it's going to become 1. So we don't want to XOR this, but then we also have to think about the XOR case. So the main thing we are looking at are these edges. So for these edges, we have two possibilities, right? Either we XOR or we don't XOR. If we have like more than one XOR, it basically falls back into the no XOR or one XOR case. So we want to look at that. So for the XOR case, well, this is going to be turned into so like if we do XOR, we'll have a sum of 1 at the bottom. If we don't do XOR, we'll have a sum of 2. Let me put this a bit more across. So for this case, if we do XOR, well, our subtree sum is going to be 2. And if we don't do XOR, it's going to be 1. So when we look at our root now, so we have two possibilities, right? Well, I guess we do have more possibilities than that. Because like right now we have like 2 states, and so for each of these we can either pick the larger version, I guess. Yeah. What am I saying with the larger version? So, well, actually, we have 4 states here that we have to deal with, right? So we have like because we have 2 options on this side, and then we have 2 options on the other side, and we want to pick the optimal of that. So actually, right now we would have 2 to the power of like however many children the next node has, amount of like operations we have to do. So we have to think of a way to shorten that, I think. So what can we do here? Let's think about it. So I think like for 1, so for the value up there, again, we only need to think about doing either 1 XOR or no XOR, right? Well, like obviously you have like more stuff on top. But let's ignore that for now. Let's just think about like that case right now. So if we do XOR on this number, well, we are going to have a 2, right? So, actually, is this only for like, is this only the top case that does that? Yes, so yeah, I'm just looking at the different possibilities up here. Because like we don't actually need to know, like we just need to know the maximum if we do like turn this edge or if we don't. So that's like those are the only states that actually affect 1. So I guess what we can do is we can get the one idea is we can just like pick the largest sum from like from each of the options. So for example, like we will pick that, and in that case, because our total number of operations are, well, like our total number of XORs used is a odd number, right? So that means our top number will also get XORed. So it will be like, 2 plus 2 plus 2. So that's the first case. The second case is we want to find the maximum where we don't actually do any XOR. I'm thinking like whether like can we put these numbers into like some sorted list or something? So like we can have that. So like we have 1 and 2. Then we can have like the cross one. So that will be 2 and 1. So because like this operation itself is a 2 to the power of n kind of operation, maybe we can do another DP that just finds the best case. Yeah, actually I think that will work. So we have a DP state within like each of these things. So yes, I'm thinking of like a DP inside a DP, which is kind of cursed. So we have like 2 things here, and then that will be like the number of children it has. So number of children. So for the first state, well actually like initially, so we can think about this as like if we do XOR and this if we don't do XOR. So initially we actually only have one option, right? So either we pick the XOR case or we pick the not XOR case. And then for the next thing, so if we want to have XOR, well, we can either come down from here, or we can so we can either choose the XOR edge, and we can like go up here, or we can choose the non XOR. Or we can choose a non XOR case, and we can go up here, and then we just take the maximum of that. Yeah, and I think that should work. So like in this case, either we pick the non XOR, so it will be a 2 here, or we can pick the XOR case. So that will be a 2 here, right? So that will be 4. So you get the maximum, it will be 4. So you have like this kind of running DP here. Yeah, actually I'm pretty sure this will just work. So it's a 3 DP, and then you have another DP to choose the best case. Well, up here. Yeah. So that was a very long explanation, and maybe I can start coding now. So do I want to write this in C++ or Python? I'm more comfortable with Python, so maybe like I spent too much time talking already, so I'm going to do this in Python today. It'll be a bit quicker, I think. I hope. Yes, so what do we need? So the first thing we need is we need to turn these edges, and I think what we want to do is we want to start from, we want to make 0, like the 0th node, our roots, because like for a tree, any node you pick, it'll become a tree anyways. So we can just arbitrarily pick one. So like I'll pick 0 in this case. So we have like parents. Yeah, so the first thing is we need to turn this edges list into some more manageable data structure. So we should have like, we can have a children array actually. Is that better? Yes, because we can recursively go into we can recursively go into each of the each of the node, and then we can just and then so after we're done with that node, we can just go back up like when we finish doing the DP and stuff. So we want the children, so it will be a list for I guess length nums, because that's the amount of nodes we have. But before that, I think it makes sense to turn into an adjacent list, so we can later on do a DFS to just find all the children. Alright. So we have adjacent list. Length nums, and so now for a b in edges, just do adjacent list a append b, and then we can do the same down here. And now we have the children array set up. We can just do a DFS now. Yep. I'm a tiny bit worried that if we have a linked list of 20k elements, that we will reach the recursion depth maximum or something. But hopefully we don't have that issue. Well, it's not an infinite recursion loop, so I think it should be fine. Well, yeah, or we can just set the recursion depth to be higher if that's an issue. So we can just start with 0. Well, actually, another thing we can do is we can just run a actually, what can we run here? Yeah, we can just start from 0, and so I guess get children. So how do you want to use this function? Well, we just want to do get children 0, and then we can just gradually go down, right? So n is the node we are dealing with. We probably shouldn't choose maybe index. So we want to do that, and then so we want to add the index into scene. So for example, when we get to the first the second node here, it doesn't think the first node is child. Well, actually a better way to do this is we have a parent up here. So we'll set it as -1 normally. For the first case. So, well, basically what we can do right now is just do for next in adjacent list. So that will get all its neighbors, right? So if next is equal to parent, well, it is its parent, so we don't want to do anything there. But if it is not its parent, so it will be its child, right? Because for a tree, every node only has one parent. So we can do children index pen next, and then we can just run get children of next, and we will set the parent to be the current node. So we can just do that, and that should get all the children for every node. Right. So what can we do next? So for the next thing, we have to write a function. So we want to like get max sum. Well, from our index. So that would be like the root of the subtree. And if we get the answer for 0, we can just return that, right? So what does that mean? That means like we just do return get max sum of 0, and that will be our answer here, right? So after we have done that, yeah, I guess like what we also need is we need a max sum DP. So that would have to store 2 numbers, right? Wait, actually, are all the numbers yeah, we can just leave it as an empty array, I guess. That will also work. So for every node, we need to have a max sum. So for each list, we will be storing 2 numbers. So the first one would be so first number would be with XOR. Second would be without XOR. Like from the top here. Right. Okay. So after we have this, so we need to think about the base case first. Like whenever we're doing 3DP, so the base case is if we only have one number, right? So if it is a leaf node, so for a leaf node, it will have no children. So children index. If not, so like that will be the empty case. So if it is empty, well, we only have one option, right? Which is to XOR or to like not XOR. So index 0 would be our number. I think it's called nums index, and XOR is this, I'm pretty sure. Yeah, and we want to XOR k with this number. Or we have the other option, which is to just not XOR at all. Well, we'll just get the number, right? So we can return. So that's our base case. If we do have children, we need to get the XOR and not XOR cases. So we have like 2 cases here. So if children, well, actually, yeah, so we just want to do for child in children of index. So for each of them, if maximum DP is not evaluated, we want to evaluate it, right? So maximum DP child. So if it is empty, actually, we should just do append here, because we haven't initialized any of these things. So we just do append. So after we append the XOR case, we'll append the non-XOR case. And right now, if it is empty, that means like we have to evaluate it first before we can add the things in, right? So get max sum child. And then like it will recursively get all the answers. So here, what we can do is, so for the XOR case, we will append maximum DP of the child. Like for the XOR case, we'll do that. For the non-XOR case, so not XOR, we'll do that. So basically what this does is it gets our DP here. So we can like form another DP inside. So DP what do we have here? So we have two rows. So it will be the XOR row and the non-XOR row. And then it will be the number of children long. So it will be so we have two rows, and then for each row, I guess we can just do that later. So like we can just keep appending, and we will just like get the answer at the end. So DP, yeah. So DP 0. So if we look back at our case, what did we append here? So well, for the first child, so it would be like the first. Well, this is like the XOR, and this is the not XOR array. So it would just be the first numbers here. So so XOR 0, and then DP1 will append XOR not XOR 0, actually. Not XOR 0. And now for I in range, 1 all the way to the number of children it has. So, well, it would just be length XOR. So for each of these cases, we want to find the best case for XOR. So XOR 0. Well, we want to append the maximum of so DP, so the last element of DP0 is going to store the best case if we are currently in the XOR case, right? So if we want to keep it to be XOR, we need to add the not XOR case. Yeah, so that's what we have here. Or well, we can get it from the non-XOR case, and we add the XOR case up here. So that's the first thing we have. So DP1, it will basically be the opposite. So we can go from XOR, and we pick the best XOR. Well, we pick the XOR case, or we can go from like non-XOR, and we also keep doing the non-XOR case. So it will be, well, not XOR. So after this, we are going to get our answers at the back here. Yeah, but remember, so like what we have dealt with before is only for the root, right? So if there are more stuff above, we still have to consider like this edge here, basically. Well, but I think like for this edge, it will just be flipping like the XOR and not XOR case. So actually, let's deal with the 0 case first. So that would be if we have reached the node already, right? So if we have reached the node, we just want to return. Actually, yeah, we can set the maximum DP. Or we can return as well, actually, like because we have gotten to the end already. Right, yeah, because like we just want to return it at the end here. So it would be the best case for if we are doing XOR. So DP0 minus 1. And because all the numbers are positive, we will never actually XOR into a negative number. Yeah. So we want to add nums index. So because we are in the XOR case, we need to add our roots value XOR k, or we can have we can do the non XOR case, and we just add our number here. Well, for the other cases, because like we have another edge up here, right? So imagine like this is not the root, and we have like more stuff going on up there. So this is like when we have to set our maximum DP of index. So the first thing we want to add is if we do actually do XOR up here, well actually it doesn't affect anything. It doesn't really affect anything down there, right? So it'll just be, so if we do XOR, we will have to do nums index XOR k, plus, because it doesn't affect anything down here. Well, actually, no, actually it does. So if the total consensus down here is that we do XOR up here, it'll be different to, like, for example, if we use like one edge here compared to like no edges, there will be some difference, right? But our starting number is the actually, yeah. So if we do XOR this number, that means we have to use the non XOR case down here. So it will be DP1. So that's the non XOR case. And the last element will store the best so far. But we want the maximum of if we do XOR here, but down here is also XOR. So it will be 0 minus 1. It will be something like this, right? And the next thing is going to be if we don't XOR. So if we don't XOR, wait, no. So this is if we do XOR down there, but we also wait. I'm getting ahead of myself. Yeah, okay. So we do XOR here because down here the consensus is that we do an XOR, or we can not do XOR, and down here our consensus is not XOR. So it will be this case here. So we will have set that, and then I think that's it. Okay, let's fix the bugs now. N is not defined. Oh yeah, of course. Linked nums. Oh, wrong answer. That's not good. Our output is well, that's quite strange, because it shouldn't do that. Get max sum. So we want to get max sum of 0, but it actually returned that thing, which is quite strange. Yeah, it should only fall into this case here. Let's see what it ran up here. So print. I guess we can just print the child to just make sure. Well, this case actually got to the 2 children. Yeah, okay, so it doesn't actually get to. Yeah, maybe we should check whether the get children thing is even set correctly. So that should be a. Yeah, okay, so this is the issue, right? So because like when we do XOR, it doesn't even update anything. Like not XOR, when we are actually trying to get children, it doesn't even do anything up here. So of course. Yeah, so it is only if it is equal to parent we don't want to do anything. Yeah, okay, so now get children is correct. So yeah, so like the 0 node has like those two. So let's go back down here. So we want to print child here. So we just want to make sure this is actually run. Yeah, okay, so now we did get that. Oh, actually it output 7. Well, the obvious thing to do here is to print out our maximum DP to see what's going on, and then we can return res. Right, so for the first node, if we do XOR, yeah, because the first node is 2, right? So actually, yes, that part is correct. Right, so that means like something is wrong up here, I think, like when we are actually adding the stuff together. So yeah, we can just go back to returning this thing, and then up here we just want to print out, I guess we can print out our XOR and not XOR thing first to just make sure, well, like these things are working. Not XOR. Yeah, so that will be 1 and 2, and that will be 2 and 1. So that's the same as what we have here, yeah? So that part is fine. So we would, yeah, so that means like some logic is not correct down here. And it will be easier if we just print out DP. Right, so it actually got to like 1, 4 and 2, 6, which is kind of not what we want, right? Like what we have here is 1, 2 and 4. Well, what should be the thing down here? Let's work it out. So this is like the non-XOR case, right? So we can pick the XOR case, and then we can add like this case here. So we have a 2. So it will be 1 plus 2 this way. So this way it will be, well, continue picking the non-XOR case. So it actually should be a 3 here. Did I add them together instead accidentally? Huh. Right. Yeah, because like the other stuff is correct. It's just the last number that's wrong. So dp1 append. I see. So instead of using this number, because we are doing append, we actually got this number instead. Yeah, okay, so that's kind of a bad mistake, but we can just do that and it should work out. So dp1, that shouldn't be changed yet. I think now it should be correct. Yeah, the better way is definitely to just like set the whole array with 0, and then like you use the index to actually change instead of doing like append. Append is not a good idea. Okay, so let's try to fix this case. So we have a 0 and 1 here. And what are the numbers? So it will be 2 and 3. The expected answer is 9. Maybe let's draw this up. So we have a 2 and a 3. Our k is 7, so it will be 1, 1, 1. Yeah, so actually in this case, either we do XOR or we don't. Is it the case where like when you only have one children, like one child that messes things up? It could be that. Wait, actually, it prints out 4 and 3 because if we look at this case here, it'll be 1 1. So if we do XOR, it will be 1 0 0. Okay, so that part is correct, I think. Yeah, that part should be correct. And then what else do we print out? Well, actually, we only have D stuff. Maybe there's an error here, maybe. So for the, yeah, actually, what will we do here? So we have a 2. If we do XOR, it's going to give us a 5. Right, okay, let's write that down. So we have a 2. So if we do XOR, it's going to become a 5. So the best case would be, it will be picking the XOR case for the best case. But what are we doing here? So we have a 4 and a 3 at the end. So this is the XOR case. And num's index XOR k, well, actually, I think what we can do is we just print out these. Because actually, like this one, I'm not too sure what actually went wrong. Well, we have 1 and 5. That's very strange. Yeah, just print out each of the terms. Yeah, so this should be a 2. That should be a 7. So that should get turned into a 5, as we have said before. And we do get a 5. Oh, what? Wait. So when we do these separately, it actually does give you 9. But then it returned a 5 out here. Huh. That is very strange. So it is suggesting that, so like my values are correct, but like when I do the max here, something kind of horrible went wrong. Is it because like I have to bracket these things together? Surely not, right? Like because when we are separating them, it could be that this term is like XORing the whole thing here. Yeah, I think so, because like there'll be a 9, and then if we actually do XOR, wait, actually, does that even make sense? I guess one way to do is like just do a bracket here. Just see if, yeah, okay, so it is a order of operation kind of issue here. So do we have any more of these things that we have to deal with? So this one is at the front, so that's fine. Any more XOR that we need to look at? Don't think so. So I hope it works now. Well, we also have the maximum DP thing that isn't included in any of the cases. Yeah, okay, so as I suspect, there will be some issue left. So our output is 256 here. So let's just use the test case. So I think right now we have to debug like the case down here. So numbers. Yeah, let's draw it out. So 0 connects to 2, 1 connects to 2. So we have like 24 that connects to 1. And then, so I guess like we can look from 2. So like 78 would be here. And then 4, 2. So that means like 2 connects to 4. It'll be 44. And then 3, 4. So we'll just connect a 3 down here. So that's what we will get. Yeah, I guess like the only like real thing we can do here. So k is equal to 6. Like really the only thing we can do is I guess we can like fix this so it is more consistent as well. Yeah. So we can just print out the maxsum dp and see like what was wrong up here. So res print maxsum dp return res. Yeah, we might have to like work out the binaries there as well, which would be kind of a pain. I'm just trying to see if there's any get around before we actually have to do that. Yeah, let's actually mark down the index here as well. So we have a 0, 2, and that's 1. That's 4, and that's 3. So for 3, is 97 XOR. So it's 97 XOR 6 gives you 103. Is that true? I think that should be correct. So 97 would be like 64, 32, and you have like 16, 8, 4, 2, 1. And then 6 is actually just 110. Yeah, so actually, yeah, it makes sense because it turns all of these into 1. So you add 6 to it. So that's correct. Wait, the output is 254 now, which is actually like 1 XOR away. Okay, yeah, so I'm pretty sure it is something wrong here then. Am I XORing the wrong stuff? So max sum dp yeah, so remember the 0 is the XOR case. So we want to get the max of our number. So this is like if we do the XOR with its parent, right? So we will XOR the number and then wait, yes. Wait, so this is the not XOR case. Yeah, which it does make sense that that's there. Yeah, I don't want to go through each of the cases because it will be quite slow. So I'll try to see if I can do by inspection first. So maximum of nums index. Yeah, so we want to XOR here. We want to XOR the number because like for its children, we are not doing any XOR. So if we do XOR like the edge with its parent, so that should be correct. And if we have XOR below, the XORs will cancel out. So that should be correct. And maximum dp index append. So this is if we don't XOR up above and we choose XOR below, we do have to XOR our number. Otherwise, we don't XOR our number. I guess let me like try this as well. if this does affect the answer, then, but I don't think it does. Yeah, it doesn't. We might have to work out. Oh, but something changed, because before I'm getting 254, right now I'm getting 256, which is very strange, right? So if I don't do the brackets and run it, yeah, it gives you 254. So actually the brackets, it does change something. Huh. Yeah, this thing is very, I don't know why the XOR thing is so fragile. Maybe I have to do a bracket up there. Okay. I honestly have no idea why. So maybe we can, if we, okay, we do pass, nice. But let's find out what the issue is here first before we talk about how I got the intuition. Um, yeah, actually, I'm not sure what's going on here. So when I don't do the bracket, let's open playground. It's always very helpful to just do this. Right. So basically, like what it is saying. So remember, like when we have the 4+5, XOR 7 case. When we have this case, right? Right, it gives 14 right now. Let's go back to, I think it was this case. Is it? Oh, I think if we do this, it'll be even faster. Yeah, but what case do we have that's wrong? Well, it is not that much faster. Is it case 2? Yeah, I think it was case 2 that's wrong, right? So we have a 4 and 5. And then when we... Well, actually, do we have a 4 and 5? Let's just print this out. So we have like nums index. Yeah, and the thing afterwards doesn't really change anything. Yeah, so we have a 5 and a 4. If we do them separately, but if we add them, it was never closed. Should we just add? Yeah, I'm just trying to be a detective and find out what the issue is here. So actually for this case it works, but then if we do this, it doesn't work. Yeah, it gives you a 1 here. But what are the actual numbers that we have up here? Yeah, so we have like 6 and I guess doing this is better. Right, so yeah, we have a 4 and a 2, and then we do XOR 7, right? So actually, yeah, it's 4 and 2 here. Yeah, so it gives you 1. So that would be 6 and 7, right? So 6 would be 1 and 0, and then 7 would be 1 and 1. But actually, if we swap these around, what is it going to give you now? It gives you a 9. So if you swap them around, it gives you the wrong answer. So let's see what kind of issue it is. Well, actually, no, 9 is the correct answer. But I think it is like for here. If we don't do bracket, the answer is just wrong for some reason. Yeah, honestly, I have no idea why that's the case. But maybe if I find out, I'll tell you guys tomorrow. So let's talk about how I got the intuition for this question first, I guess. So, well, the first thing to notice, like as I mentioned before, is that you have the like a number XOR another number, and like if you do two XORs on the same number, it gives you the number back. So that kind of eliminates the any number of times kind of issue, like where you can potentially have like a million operations or like 10 million operations. So that's the first thing to notice. The second thing is like yeah, I think the second thing to notice is that you have the greedy problem. So like for example, if you do XOR this number up here, so maybe I'll go back to the so what I'm talking about is this case. Yes, this case here, right? So when you have like when you're looking at this number, well actually yeah, if you do XOR like on 101, which is a 5 here, if you do XOR, it is going to give you a better number, right? So like you went from 9 to 12, but then you have another number that you're affecting. So whenever you have like some kind of side effect when you're doing greedy, you have to really think about whether the side effect is also optimal or not, or like whether it could be eliminated. So in this case, no, we actually don't know like whether it could be eliminated or not, because like what the other number is would affect whether like choosing this edge is actually optimal or not. So when greedy doesn't work, DP should be the next thing that comes into mind. And actually, yes, like if we look at DP, it does, like if we look back up here, right, it does make a lot of sense, because like we don't actually need to know what the we don't actually need to know what the subtree or like the children's subtree are doing, right? The only thing we care about is the like is this connection here. Are we using this edge or not? Like if we are using this edge, what is the maximum down here? If we are not using the edge, what's the maximum down here? So that leaves us with a node. So like let's call this like K. So that's our parent node, right? And then it has like a bunch of children. And we don't really care about the subtree down there, because it doesn't affect the parent. The only thing that affects the parent are the edges that connects to the parents. And of course it will have an edge that connects to, well, its parent, right? And that edge will affect the parent. So here we just want to know, like, we just want to know whether we what edges we want to pick on this layer. But actually, like even that, there will be way too many cases, right? Because for each edge, we can either pick it or we can not pick it. And when we have like a 2 to the power of and kind of operate like kind of time complexity, well, what can we do again? We can do DP again, because like for DP we can kind of like cache the most optimal answer so far. So like for example, for this edge, well, like let's say we look at the third edge, right? Well, first of all, they are more or less independent, and also like we can use the fact that if we pick a odd number, I'll call these like the children edges. If we pick an odd number of children edges, we have to XOR our parent. Otherwise, we like if we pick an even number, we don't XOR our parent, right? And the second thing is whether we XOR So we have like some kind of like running maximum here already. If we choose this edge, it's just gonna flip whether we are going to XOR a parent or not. If we don't choose it, it doesn't change. It doesn't change like anything, like whether we're XORing the parent or not. And well, again, like we only really have two outcomes, right? So the first outcome is like we do XOR our parent. The second is we don't XOR our parent. So like if we're just thinking of like down here, well, actually a DP does exactly that. So like so that's why I thought of like using DP here, and we have basically like turned the time complexity from like to the power of n all the way down to n, and that would be fast enough, right? Um, yeah, and of course another thing to notice is that for each node, it can only have at most one parent because that's how a tree works. So when we are dealing with these edges, so that the parent edge, well, we only have to consider whether to pick it or not. And if we have, and like, and again, this edge, it doesn't care about what's happening down here. It only wants to know whether we are doing XOR or not on our current node. And we just want to pick the best option. And like we really only have two options to choose from, whether to XOR or to not XOR. So I think like that's really like the recurring theme of this question. Like you have to know that like for XOR, like if you XOR the same number twice, it gives you back the number. So I think that's like something that you really have to know for this question. If not, it's basically not doable. But yeah, I think this question is really good. Like using a 3DP, and then within the 3DP, you have to use another DP, which is, yeah, it's a well-deserved hard question, and I think it's pretty fun to do this question as well. So yeah, if you've gone up to here, well, wow, thank you for sticking with me for like 17 minutes. Or if you skip ahead, it's also fine. That's what the timestamps are for. But yeah, if you have any comments, please tell me below. And thanks for watching. I'll see you tomorrow. Bye.